Stranded in the open, dried out tears of sorrow, lacking all emotion, staring down the barrel, waiting for the final gates to open to a new tomorrow, moving with the motion, following the light that sets me
All right, good evening, everybody. Good evening, good evening, good evening. How's everybody doing here today? I hope everybody is well. We'll be starting here in just a few minutes. Hopefully we'll have people on by. Hey, Bill, how we doing, my friend? I hope we're doing good, my dude. Good, good, good. We'll wait for a few more minutes here, Bill, and then we'll go ahead and get started. Today's section is not very long. I can guarantee you that. It won't take us too long to get through stuff. I think it took us like, I don't know, 40 minutes max to get through this next section. So, shouldn't take us too much time to get through everything, and should be good to go. Surprisingly, there's not a ton of content, but yeah, you know. Still gotta get through it nonetheless. You can believe it. We are, after today, there will be just one section left. And then we're done. I know. We're already there. Getting very, very close. How's your week so far, Bill? Hopefully your week is going well. Got a busy weekend ahead of me. Alright. Got some... Okay. Hey, Sammy! Sammy, how we doing, my friend? Pretty ready to start the weekend and get back to work? I can imagine that. Making the monies. Sammy, hello, good evening to you. How we doing? How we doing this fine weekend? Hopefully we're doing pretty well. Hopefully you're ready for another easy day, easy life sort of section. Yeah. I'm very good. I'm very good, Sammy. Doing very good. Been a chill day. Everybody's been sitting and relaxing, having a nice time. Not doing a whole lot. I'm not doing a whole lot. I'm just sitting and chilling. Being the best that I can be. Hopefully you are the best that you can be. That is the goal. The goal is to be the best that you can be. That is the goal. We're going to get started here in just a couple minutes, guys. We'll wait for a couple more people. I see the regulars coming on in. So we're getting there. Got you, Sammy. Got Maritza. Got Bill. We'll see if the others decide to come on in just a few minutes, and then we'll get going. Give it another minute or two, and then yeah, we'll do what we need to do. No, that's not what I wanted. Come on back. Oh, stop. Right. This. There we go. That's what we need to do. Hey, Strolling, my good friend. How we doing? Good evening to you. How we doing? How we doing? How we doing? Hope we're doing well today. Hopefully we're sitting and chilling, having a nice time, relaxing. Good, my friend. Good. That is fantastic to hear. Alright, we're going to get started here in just a moment. I think we have most of the usual suspects, which is good. Looking forward to this session? Well, today's session will be pretty short, but I think it'll be just as fine. Shouldn't be too much to do, honestly speaking. Honestly speaking, not a whole lot to do. But hey, second to last lesson today. And then there you go. Next time will be the last section in the textbook. So, yeah, we are almost there. All right, let's do this, ladies and gentlemen. Let's do this. All right, let's do it. Go. Let's get going here, ladies and gentlemen. Okay, let's do it. Okay, let's get started today. Welcome back to Thursday. End of the week time today. So today, ladies and gentlemen, we are doing section 4.3. Now, section 4.3 is going to be dealing with another concept that we have not talked about so far. We've talked about a couple of concepts here in chapter 4. We've talked about the linear correlation coefficient. We've also seen the relationship between two things of, say, x and y. We also looked at what the line of best fit is. And now we're going to include something that will hopefully tie all of the things we've talked about here in the first couple of sections here together in one more new concept here today that will certainly provide a little bit more insight. So let's go to the big board here. Let's see what we're talking about. Okay, here we are. Alright, so today we're going to be doing section 4.3. Alright, so let's go ahead and reiterate a couple of things that we had discussed here from before. So some of the things I'll talk about will be pretty much the same stuff that you've heard before, but now put with a slightly different, with something a little different, but not too much. Alright, number one, what are explanatory and response variables? So the x values here that we have, again, we have an x and a y. The x values here will be the explanatory variables. The y values here will be the response variables. Obviously, as we know, we plug in a value in for x, okay? And again, they call that an input, and we get something back out for y. And that would be the response variable after putting said input in. Okay, now that's all well and good. But the concept that we're going to talk about here today in the relationship between x and y, because that's what we've been focusing on here, is like what kind of relationship and exactly how close that relationship is what is the coefficient of determination. Now, the coefficient of determination explains how well the line of best fit works with the dataset, i.e., how well the variation in the residuals is best explained by said line of best fit. Now, we talked about residuals last time. Alright, which we said, okay, we took a look at okay, the residual is equal to the observed, again, whatever we got in the data set, minus the model, which is what we based off the line of best fit. We said, okay, observed minus the model. And we said, hey, does the model either overestimate or does it underestimate, okay, depending on that data item in the data set. And so we actually have a metric to see how many data items within the data set would be best explained by this line of best fit given that kind of margin of error. So if we're given a margin of error, again, the line of best fit doesn't go through every point. But let's say, how well can that line of best fit best explain the data set and how much percentage of the data set kind of fits within that margin of error in that for that particular data set is what the coefficient determination is talking about. So again, we have another metric that just has a slightly different meaning, not a big different meaning, but again, gives us another clear clue about how to go ahead and find that out. All right. So we've seen already, again, positive linear relationships, negative relationships. We've seen those types of things. Again, now we can see how well that line of best fit will work in the grand scheme of things. Now, to kind of further elaborate on this, let's look at number 3. Number 3 says, what does coefficient determination actually mean? This is the measure of the proportion of total variation in the response variable that is explained by the line of best fit. So, again, another just way to kind of express that here says, hey, I got a margin of error with this line of best fit. Exactly how much is explained by that variation in that data set, what kind of proportion that we have. So one thing that I want to point out here is the notation. Now the notation here is r squared, okay? And it's exactly as it sounds, okay? R squared effectively takes our coefficient, our linear correlation coefficient, and essentially squares that value. That's where you get r squared from. So the notation is pretty literal in the way it's actually shown out. Now, essentially, here's what it boils down to. Let's say we had an r squared of a random decimal number here. We'll call it 0.9614. If we had a random decimal number here of 0.9614, what would that mean in terms of its interpretation? In terms of its interpretation, we would say 96.14% of the variability in y is explained by the line of best fit. So again, this is always in relation to y, again, the response. 96.14 of the variability in the y variable is explained by the line of best fit. Okay. All right. Any questions so far about that? Any questions so far? Any questions so far? No questions. Okay. No PD? All right. Okay. Now, let's take a good look here at one more question. We'll look at number 4 here. No? All right, good. So let's take a good look here at number 4. Number 4 says, how do we determine if a linear model is appropriate? Now, we've already seen a way if a linear model actually, a linear relation exists. We saw that back in section 4.1. We'll look at something like that here today as well. But if we're talking about the overall aspect of if a linear model, if a linear line of best fit is appropriate for the data that we've collected, it says a linear model is appropriate if the correlation coefficient R shows a moderate to strong relationship, so it has to be a pretty good R value, between both variables, along with a good coefficient of determination R squared. So if our R squared is pretty high, and we have a good correlation coefficient, again, whether it's close to -1 or it's close to +1, if it says that moderate to strong kind of relationship, then that would indicate that a linear model is very appropriate for that data set. But that can easily be changed. Again, we got to be a little careful about that. So that's why we go ahead and do our checks and balances. All right. Well, having been abstract like this is all well and good, but we need to be a little bit more direct and concrete. So let's go ahead and look at an example here. Let's see how we can met this out. Okay. So, first thing I want to show off here is to show you exactly how we can find our our r squared variable here. So we're going to do number 15 here. Let's go ahead and take a look at this. So this talks about Old Faithful. There's another Old Faithful Kaiser in Calistoga in California's Napa Valley. This is true. Surprisingly, I remembered that I went there before. It's pretty sad, but it is a place. All right. So first things first here. I would like you to go ahead and I'd like you to take out... Let's have you guys take out your calculator. All right. Let's have you guys take out your calculators here. Please, let's see. Please type Taco Bell in the chat once you have your calculator in front of you. Please type out Taco Bell in the chat once you have your calculator out in front of you. All right. So let's make sure who has their calculator and who does not. Let's bust out this key button press this time here. Okay, Strolling, Bill, Sammy, and Maritza. Okay. If there's anybody else that I'm missing here? No. Okay. All right. So now that all of you have your guys there, let's go ahead and move that over for just a second. Just move this to the right. And make this bigger too. Should be a bit easier to read. Okay, so first things first here, we're going to go ahead and hit the stat key on our calculator. And we're going to go over to edit. Now again, if you have values here, again, go ahead and clear them out and hit enter. Go ahead and hit clear and enter. Okay. And list one will be all the times between the eruptions. So let's put that in for the X values here. Did I skip one? Let's see if I skipped one. 11.3, 11.7, 3.5. Oh, no, there are 9. Never mind. Alright. Alright, once you guys got all your numbers, hopefully your numbers will match what I have up here on the screen. Once your numbers match up, or if you've entered in all your numbers here that look exactly like what I have up here, please type in Polish hot dog. Alright, please type in Polish hot dog. We will we'll move forward after that. Type in Polish hot dog. Once you guys got that here, you got your numbers in. Thank you. Thank you, Bill. Thank you, Strolling. There's Sammy and Maritza. Alright, Polish hot dog. Alright, good. Sammy. Let's see if Sammy's got all the numbers entered in, and we'll move forward. Okay, so I'm not sure where Sammy went. Maybe Sammy took a step away. I'm not sure. But okay. We'll wait for... Oh, there's Sammy. Alright, there he is. Alright. Okay, so everybody's got their numbers entered in. Let's go ahead and go to the next part here. Alright. So, next part here is we're going to go ahead and hit the second key and the mode key. Quit to the main screen, just making sure we don't enter anything bad. Alright. Let's go ahead and hit the stat key here. Gonna go to calc. Gonna go to number 4, which is Linrig. ax plus b. So again, go ahead and enter this in. We've done this before, but again, just as a further reminder. Again, if you have the old school calculator here, with linreg ax plus b, remember it'll be L1, comma L2. Okay, so again, if you don't see anything in the X list, just hit second and 1 for L1, hit the comma key, second and 2 and for L2. And if you don't see anything here, second and 2. Frequency list, just leave. If you have this menu here, again, just leave the frequency list and this, whatever this is, blank. Just leave them alone and go to calculate. All right, very good. All right, so this is what we should have here for our numbers. All right, so let's type in unlimited breadsticks. All right, please type in unlimited breadsticks. If you got the same exact numbers that I do here on the screen. Unlimited breadsticks. That's not my problem. Just because I happen to urge hunger pangs, you know. I was just waiting on Sammy here. Sammy, hopefully you got the same numbers that I do. Just type in unlimited breadsticks 1, 2. Yours is wrong. Okay. Well, we need to look back at the numbers here. No breadsticks for you. That sounds so mean. Alright, so did you do linreg ax plus b L1, comma L2? Asanla got it, okay. So let's take a look at your numbers here. You should match the same numbers that I have here on the screen. So take a look and make sure all the numbers are correct. There's Sammy. Tanla made it, that's good. Unlimited breadsticks. Like, there's nothing wrong with that. Make sure all the numbers there are exact, my friend. And let me know once you got your numbers there, Sammy. And we'll look at the other half. Oh yeah, I better bring that up while this is going on. I need an R squared. It would be helpful if I have R squared. Unbelievable. Sammy, are you there? I'm not sure what's going on with Sammy. We'll come back to Sammy here, hopefully, when he decides to hopefully figure it out. Alright. Oops. I didn't mean to do that. Alright. Let's go to the, again, Sammy, once you have your thing, go to second, go to calc, number 4, linreg ax plus b, L1. Yeah, buddy, you gotta tell me a little bit, there. What seems to be the trouble? Do you have linreg ax plus b there, Sammy? It's kind of important. I'm not sure. I can't see your calculator, obviously. So I just want to be sure that you do, again, linreg ax plus b, L1, comma L2, if you have the old school calculator. If you have the new school calculator, this is what it should look like here. So you take a look at the screen. On your list, you should not have anything for frequency list, and you should not have anything for this other thing. These things should be empty. The numbers are just off by a little? Yeah, you can't have your numbers off by just a little. You gotta do the right numbers. Okay, that was the problem. That was the numbers were off. Be sure to type that in again, okay? Alright, go to calculate here. Now, we've done stuff with the numbers here so far, ladies and gentlemen. We've done A and B here. Remember, A was our slope of our line of best fit. B was our y-intercept. We also have R here, which is our linear correlation coefficient. But we also have this R squared. And we have this R squared specifically as 0.8298. Okay. Alright, so 0.8298. Now, if this is 0.8298, then what does this reflect? This reflects that we have 82.98%. So we'll just go back to the handout here for just a moment, and we'll use it in the context here. Again, if we're going to do this right, it says 82.98% of the variability. And again, this is going to be in variability. 82.98% of the variability in this case, what's the context? Let me put the context in here. In the length of the eruption is explained by the line of best fit. Okay. Oh, you got it? Okay. Cool, cool. Nice. You may now have unlimited breadsticks, alright? You may now have unlimited breadsticks. Alright? That's good. Sam, you got unlimited breadsticks. I'm very happy to see that. Okay. Alright. Alright, so 82.98% of the variability in the length of the eruption is explained by the line of best fit. That's how we best describe this this guy right here. Alright. Are there any questions about how we found R squared? If you have no questions, copy and paste the following. Okay, it would be very helpful. Please copy and paste the following if you have no questions. That would be wonderful. Then I know that you got it. Perfect. We'll move forward. Strolling, you look like you have a question. Although you said pneumono ultramicroscopic silicovolcanoconiosis, of which I'm very proud of you. Go ahead, my friend, go ahead. If you have questions, it's just fine. I'm here to answer them. It's a real disease, by the way. I'm just going to point that out. You can Google that. It goes beyond the borders of the Google word finder. But it's a real-life lung disease. Oh, okay. The meaning of A and B. So if we go over this, the meaning of A, remember we have y equals ax plus b. So A is the slope. So A is the slope, and B is the y-intercept. That's the meaning behind A and B, respectively. So It doesn't tell you mx plus b, because that's, I know most people are used to mx plus b, but again, a would stand for the slope, the rate of change, and then b would be the y-intercept. What happened? What would the value be if x was 0? So just like its normal meaning in like regular algebra, same deal. No difference, I promise you. Okay. Now, what I want to do next is I want to go over a couple of examples with you here from the homework, just to cover a few more bases in regards to several things that we've talked about here in this chapter so far, because this section also serves as a way to kind of put together a lot of the concepts we learned in 4.1 and 4.2 as well. So let's go ahead and take a look here. I'm not going to go over everything, but I'm going to go over most things. So let's talk about it, and we'll take a look. Okay, so let's take a look at this particular example. This particular example says the following data represents the time between eruptions and the length of eruption for 8 randomly selected eruptions. All right, completes part A through C. All right, so it says what type of relation appears to exist between eruptions and the length of the eruption. So let's look at the scatter plot. All right, so here's the scatter plot. So what do you guys think? Based on this scatter plot you see here up on the screen, would you pick A, B, C, or D? Pick A, B, C, or D. A linear negative association, a negative linear, a positive linear, a nonlinear, or no association. What do you guys think? A, B, C, or D? Go ahead and put your guess in the chat there. Alright, Bill, Sammy, Strolling. Let's see if we have Maritza and Sanla here. Maritza also says B. Alright. So it looks like everybody's been saying B. Alright, that's perfectly fine. Alright, so let's put in a B. B is correct. Okay, again, if we go up here, again, notice it goes in a positive pattern, moving up, trending upward. So let's pick B, check that answer, and that's correct. Okay, that will be correct. Alright, so there's that. Does the residual plot confirm the relation between time of eruptions and length of eruptions is linear? So does it confirm that it's linear here? Now let's take a look at the residual plot of the data here, as we're going to need to make a note in regards to this. Okay, so this is a part I have not talked about here yet, but it is important that you do make a note of this. Now, this is the residual part. Now, remember the residuals, as I mentioned here earlier, again, is taking the actual observation and subtracting it from the model, okay, the line of best fit, i.e., and then seeing what that difference is, whether that difference be positive or negative. So here's how it works to see if there's really a linear relationship or not. All right? So if the residual plot does not have a pattern, then the variables are linearly related. So it seems a little strange, but if the residual plot does not have a pattern, if there's no pattern at all, like they're just kind of free-floating points out in the middle of space, then the variables are linearly related. So that's something that you may want to copy down, so that way if they do ask you this question, you'd be prepared to answer that pretty easily. Okay, so if I looked at this scatter plot here, and I looked at A, B, C, and D, which answer would we have here in this case? We have A, B, C, or D. Which one would we have here? Would be a linear model be appropriate here in this case? A, B, C, or D? What do you guys think? I just want an answer here. Give me a guess. Give me a good guess, hopefully. All right, Strolling says B. Okay. Let's see what the others have to say. I'm not going to answer for you guys. You guys got to answer for me. That's how it works. Sammy says D. Bill says B. All right. How about Maritza? Maritza says B. A little unsure about that. Sanla? If you're still there, Sanla. Okay. Sanla says D. Alright, let's take a good look here. Now, first of all, both of you have said there's no pattern to this, right? There's no pattern at all. Let's read what it says. The plot of the residuals for D, it says plot of the residuals show no pattern. That implies that they're not linear related. Now, read carefully. Read carefully what I just wrote up above. Okay? So what I just wrote up above was this. If there's no pattern, that means they are linearly related. So this is one thing you have to be careful about. No pattern means yes. If we have a pattern, that means that you could be increasing over and over and over again. Your residual keeps going up or your residual keeps going down. Does not indicate an actual pattern of a linear behavior. So we want to be sure that there's no pattern whatsoever. So the answer is indeed going to be B. There's no discernible pattern, so a linear model is appropriate. Okay. So that's that guy right there. Okay, questions about that? Any questions? Just want to be sure. Any questions about that? Before I move to the next part. Okay. All right. Okay, next. All right, this one here asks, the coefficient determination is found to be 88.6%. Provide an interpretation of this value. All right, so basically, at the end of the day, this one's actually pretty silly in some respects, but again, this goes back to our interpretation that we talked about before. So it says the least square regression lines explains. Now, what you want to put in this blank is just the same percentage that you have up above, 88.6%. So, the least square regression line explains 88.6% of the variation in. And in this case here, you always want to put the Y value here. Though the Y value is the length of the eruptions, as it says here, the length. So we're going to put the Y value here, variation in the length of the eruptions. And we'll go ahead and check answer, and that's correct. Okay, so we have that. So that will end question number 15. Okay. Alright, so that's how we go ahead and provide that interpretation using our coefficient of determination. Alright, easy peasy lemon squeezy, no problemo. Alright. Hopefully no questions about that, otherwise I will move on. Alright. No questions? Otherwise, I'll just move on to the next problem once you guys, if you say no questions, we'll be good. Okay. Okay. Now the next one here that I'm going to do for you guys is I'm going to do number 17. Okay, so let's do 17 here. And this is going to tie a lot of the concepts that we've talked about here in chapter 4 together in kind of one question. So a lot of different things here that's going to be going on. Like I said, I'll be skipping a couple of parts here in this question because there's a few more that I want to focus on. So okay, I'm going to make this a bit bigger. I'll have to shrink this down a smidge. Keep forgetting that the thing we need to look at is always in the corner. Alright. Okay, so here's our question. Let's go ahead and read this off together here. So, the following data represents the number of calories per serving and the number of grams of sugar per serving for a random sample of a high fiber cereals. All right, so here are some calories. Here are some sugars associated with it, and again, here is a scatter plot for that. Okay, so let's look at letter A. A scatter diagram of the data is shown. So that's this guy right here in the corner. What type of relationship appears to exist between the calories and sugar content? So A, non-linear, B, no relationship, or C, strong. Strong linear. So what do you guys think? Be A, B, or C? What do you guys think? A, B, or C? A is non-linear, B is no relationship, little to none, or C, a strong linear relationship? Think a strong linear relationship? Strong linear relationship? Alright. Maritza says C. What are some other guesses here? A non-linear relationship? Okay. A is not equal to B, no. Non-linear would mean like it looks like a parabola or something like that, Strolling. So if it looks like a parabola, or it looks like any other curve that's not a line, that's a non-linear relationship. B would mean that there's little to no relationship, meaning there's no discernible pattern whatsoever. Alright, that's the difference between A and B. A says there is a pattern, it's just not a line. B says there's just no pattern at all. Alright, Bill says B. Maritza's just changed her mind again from C to A to B. Alright, Strolling says B. Okay, let's see here. Okay, we have Sammy and Sanla. Sammy says B. What does Sanla say? Sanla says B. Okay, and that is the correct answer. There is little to no relationship here between calories and sugar according to this. All these points are kind of all over the place, okay? There's no really discernible pattern whatsoever that we can get. No linear pattern even. So that's going to be our answer here. There's no relationship that we can establish. Okay, so the next thing is going to ask you for the correlation coefficient. Now, you could do this in the calculator like we already did. I'm going to skip this part here because I'm not going to go over this. This is, we've already talked about how to do that from our first example here today. We can find the coefficient determination right below it is what R is. So I'm going to skip that guy, but we will use the answer here, certainly, in the next question. All right. In the next couple questions, I should say. So I'm going to make this a smidge bigger. Okay, next. Determine the critical value for the correlation coefficient. So we're going to determine the critical value here for the correlation coefficient. Now, if you recall, this guy has some stuff to do with what we talked about in the first section of Chapter 4. So the very first section here of Chapter 4 is that, if you remember, we talked about, we look at this little book, it says the critical value table. Remember, it's dependent on the sample size, and then the critical value is right next to it. Okay, so first of all, let's ask this question here. What is the sample size? What is the sample size? What is the sample size here? How many points do we have according to what we see in the data set? So what's the sample size that we have here, guys? The table is right here. I know that's covering the scatter plot here, but I'm talking about over here. You can look to the left there, Strolling. How many points do we have? The answer is 5. So if we have 5, what's our critical point? What is our critical value, excuse me? What is the critical value? 0.676. 0.811. N is equal to 5, guys. There's a number next to 5. It's not 0.811. 0.878. There we go. I was like gonna think about it. I'm like, you got a number next to that. Like, numbers are very tiny. This is as good as it's gonna get for now. Unless I can make it bigger. There. I made it slightly bigger. Alright. Let's check this answer here. Alright. Okay, next. Go to the next part here. Alright. Is there a linear relation between calories and sugar content? Is there a linear relation between calories and sugar content? Now we can pick A, B, C, or D here, okay? Now this also goes back to what we talked about here in section 4.1, all right, where we actually compare the critical value and the correlation coefficient. So if you recall here, remember that the absolute value of the correlation coefficient has to be bigger than the critical value. All right? That's what has to happen here. So if we take a look at that here, the absolute value of the correlation coefficient has to be bigger than the critical value. So let's see what happens. Let's take a look at each answer here. So it says, since the correlation coefficient is less than the critical value, there's not a linear relationship. If it's less than the critical value, there is. If it's greater, then there is. If it's greater, then there isn't. That's A, B, C, and D here, respectively. Remember how it works. Again, if it's bigger than, then there is. If it's less than, then there isn't. That's how it works. So which one will it be? Will it be A, B, C, or D? All right, Strolling says A. All right, let's hear what everybody else has to say. All right, Maritza says A. Bill says A. All right, let's take a look at A. Again, it says if the absolute value of the correlation coefficient is less than the critical value. So 0.204 is definitely less than 0.878. So there is not a linear relationship between calories and sugar content. That's correct. Very good. That's right. Okay, let's look at the next part here. Next part. Okay. So this next part here may seem slightly a bit confusing, but here's all it's asking you to do. I'm gonna have to shrink this down a bit. Make it fit. Alright. For just a second. Alright, so this, they ask you, okay, hey, I'm gonna include a new point. Now this new point here is if we're at 50 calories and 3 grams of sugar per serving. Okay, so this is the new point that they throw us in here for. And they say, okay, well, what's the new scatter plot if we include this new point? Okay, that's basically all they're asking us to do. So let's take a good look here at the original graph, the original scatter plot. So here you can see the original scatter plot, which is this guy right here. Again, calories on the bottom and sugar on the left. Okay, so again, our answer here should have calories on the bottom and sugar on the left. So we're going to automatically eliminate A and D because that has the wrong places. So the only two answers we're going to get here is going to be C, B, and C. And it can't be C because it doesn't look like what we have up here in this corner. So it doesn't look like what we have in this corner here is what C is. So we're going to choose letter B. Letter B is our best answer that we can choose that matches the graph. And I need to make it smaller because I don't know if you can completely see that. Maybe this would be better. I wish it wasn't in the corner. Maybe I can put it here. This is what it looks like on the basic graph. And you can see letter B is very similar. Again, where the points are. And here's 50, 3 right here. A little tough to see, but that is what it is. I can't put up two graphs at once. That's unfortunate. Alright. I'll put this graph up and you'll see. It's pretty much the same thing, just again with that extra point. So we'll guess B, and we got it. Okay. To the next part. Alright, next part, they're going to be asking for the correlation coefficient. Again, same stuff as we did before, so I'm just going to skip this. Alright, so you just add the new point in, and then you find the correlation coefficient. So they found it as 0.875. Alright. Now we want the critical value here. Now the critical value here, let's answer it this time. Let's take a look at what is our critical value according to this table. What is our critical value here? What is our critical value? That is correct. Critical value for n is equal to 6 will be 0.811. That's right. Since we added one more point to the pool, we went from 5 points to 6 points. That's correct. Very good, Strolling. That's exactly what we're going to put in here. 0.811 will be our new critical value. Since we added 1 point, that changes the critical value. Alright. So, with the new added point, let's put this down here. With the new added point, is there a linear relationship between calories and sugar? What do you guys think? Is there now a relationship between calories and sugar? We have A, B, C, and D. A, B, C, or D here? The first one says if it's greater, there is not. Second one says if it's less than, there is not. Letter C says if it's greater than, then there is. E says if it's less than, then there is. Okay, Strolling says C. What does everybody else think? I want to hear everybody's answers here. Let's take a look at everybody's answers. Bill, Maritza, Sanla. Sammy. Okay, Sammy's still there. You guys take a reasonable guess. Bill says C. Okay. Again, we're comparing these two guys here. So we're saying, again, 0.875 and 0.811. Those are the two numbers we're comparing here. So the absolute value of that, obviously. Alright, Sanla says C. Alright, Maritza, what do you say? Maritza says C. Alright, Sammy says C. Okay, good. Alright, very good. Very good, everybody. Alright. I like what I see here. Alright, so that's the correct answer here. The answer is indeed C. Since the absolute value is greater than the critical value, there is definitely a linear relationship here. 100% right. Okay. There's a couple more parts. One more part, maybe. Alright, let's take a look at this part here. Is the new point an influential observation? Now, basically, I'll just answer this question here for you guys. The answer in this particular case is that we went from having a no relationship at all, and then we included one more point of this, 50 and 3, and then suddenly it went from not being related at all to suddenly having a linear relationship just based on our testing standard. Okay? So, since it wasn't linear related, okay, so since the variables, so this basically says, since the variables appear to be linear related when they were not before, there is evidence to support that the new point is influential. So it was definitely influential. We went from not related at all to suddenly being related by including one more point to the mix. Okay, so it's very influential in that regard. Now they do ask us one more question here, and let's go over the choices here for this question. So letter D says, why is it necessary to show a scatter diagram with the correlation coefficient when claiming that a linear relation exists between two variables? Okay, so the scatter diagram, if you see here, that the influential... So I want you to take a look here at these answers. If we have an influential point, let's say the one that changed from not being related to related, that point can decrease substantially, it can increase that substantially. Basically, it can swing the numbers in many different directions. So it has a very large factor into determining if we have a relationship or not. So A and C here would say decrease substantially, increase substantially, be like, okay, yeah, it can do either one of those things. That's true. This can also give insight to data outside the range, like outliers. So maybe that's an outlier piece of data. Okay, that can also be cause a very large effect on our data set. So the answer to this is all of the above, is that it can affect it either up, it can affect it significantly higher, significantly lower, or again, tells us about data outside the range for the rest of the sample. Okay, so the data may appear linear when they're only linear for a specific range. Okay, so that can happen, and we'll check that, that's right. Okay, any questions about that example? Any questions about that example? Okay. All right. So, if there are no questions here, that is the end of section 4.3. That's it. That's all we have to do, I promise you. That is the end of section 4.3, ladies and gentlemen. That is it. All right. So, just as a friendly reminder here for next time, remember that next time I will be making a very large announcement here on Tuesday. So, and I'm going to leave you on a cliffhanger for Tuesday. This will be a big announcement here, but I need to make that announcement after we're done with this final section here in Chapter 4. So once we go ahead and make that announcement, we'll make that announcement once we're done with that material. All right, everybody. Wonderful job today. You all did really, really good here today. Again, absolutely great job. All right, but you're done here for today. So I want to thank you all very much for coming on out here to the stream today. Thank you so very much. You all are absolutely wonderful people. All right. And as always, everybody, as always, like I say to everybody here, stay safe, stay healthy, but most importantly, stay sane. All right. Have yourself a great weekend, everyone. All right. Maritza, have a great weekend. Strolling, have a great weekend. Sammy, have a great weekend. Sanla, have a great weekend. Bill, have a wonderful weekend. I hope all of you enjoy yourselves here. Enjoy your time. Relax a little bit. All right, get a little food in you. All right, thank you. Thank you so much, everybody. Take care of yourselves, and we will see you on Tuesday. Tuesday, everybody. Let's come back on Tuesday. All right, last section of the textbook on Tuesday, I promise you, and big announcement. All right, guys. Have a great one, and we'll see y'all later. Take care of yourselves, everyone. Bye. Bye, everybody.